So let's talk acceleration. Now what is this acceleration? Essentially, acceleration is a measure of how rapidly, how quickly velocity is changing. So the faster the velocity changes, greater the acceleration. So in a sense, it's the rate at which velocity changes. So, we'll define acceleration as the rate of change of velocity. Now, it is possible for us to define acceleration in two different ways. The first way of defining acceleration is to define an average acceleration, which is essentially equal to change in velocity divided by the time taken for this change to happen, and that's average acceleration. Now, for example, at time equal to 0, the velocity of an object is, let's say, 10 meter per second, and then at time equal to 5 seconds, the velocity happens to be 50 meter per second. Now over this 5-second interval, the average acceleration would be equal to the change in velocity, that is 50 minus 10, divided by the time it took, that's 5 minus 0, and that's 40 by 5, that's 8 meter. Now what's the unit? This is change in velocity, that's meter per second, divided by time, which is second, and therefore the unit ends up being meter per second square. So that is average acceleration. But then we have taken a large interval here, calculated the change in velocity over that large interval, and divided the change in velocity by the amount of time in that interval to get the acceleration, the average acceleration. Now, if you're interested in calculating acceleration at a given instant, like we did with the velocity, we first described average velocity, which was described over a large period of time, and then we described instantaneous velocity. Similarly, we will be defining instantaneous acceleration now. We've defined average acceleration over a large period. We will now describe instantaneous acceleration at an instant. Now, again, an instant is 0 time, and in 0 time there will be 0 change in velocity. Clearly that doesn't work. So what we'll do is we'll take a very tiny amount of time, something like dt, which is very, very, very small but not 0, and if during that interval the change in velocity is dv, the corresponding change in velocity in that time interval dt is dv, then acceleration, the instantaneous acceleration can be defined as dv by dt. Now remember, acceleration is also a vector quantity, so when you get a result for this, you will get it with the correct sign. Now, for instance, if the relation between velocity and time for a particular motion is 2t square plus t, then the acceleration at any given instant can be calculated as dv by dt at that given instant. So dv by dt here comes out to be 4t plus 1. And so if we are to calculate acceleration at time equal to 2 seconds, we can substitute 2 over here. 4 into 2 plus 1, that's 8 plus 1, 9 meter per second square. And that defines for us the instantaneous acceleration. Now, now that we have defined acceleration, we might as well start looking for a relation between the various quantities that we've been discussing so far. Instantaneous acceleration, instantaneous velocity, instantaneous position. How are these quantities related, and what will be the graphical graphical representations of the variations of these quantities, etc., etc. So, to start with, what we will be doing is we'll look at the acceleration versus time graphs and look at their geometrical interpretations. Also, we will look at velocity time graph one more time and see how it is related with acceleration. So, calculating acceleration from VT graph. We just learned how to calculate acceleration when VT relation was given. Now we are going to learn how to calculate acceleration once the VT graph is given. Now we are fairly conversant with this. dv by dt would actually be the slope of the V versus T graph. So all you need to do is to calculate acceleration at any given instant, just calculate the slope of the VT graph and you're done. So just a few examples of VT graphs. Have a look at this. This is V, this is T. What conclusions can we draw? This VT graph is a straight line here. So the slope is constant. If slope is constant, that means acceleration A is constant. Also, what we notice is that the slope is positive. So that means A is positive. Acceleration is positive, which means it is in the positive direction of x-axis. Look at another graph here, V versus T again, and this time again we have a straight line, but it's a downward sloping straight line, which means since it's a straight line, A is again constant because the slope of the graph is constant. And because the slope is downward, it's a negative slope, that means A is negative, which means it is in the negative direction of x-axis. But this will happen, this kind of graphs will come up when acceleration is constant. If acceleration is variable, we will get graphs which will be curves. So these are two graphs with the constant acceleration. Let me now show you graphs having variable acceleration. Now in variable acceleration, the slope of these graphs will be variable. For example, have a look here, V versus T. Now if I draw the graph of V versus T in this manner, what we observe is that there is a downward sloping graph, so A is negative all this time. And what is happening to slope? Well, the graph is becoming more and more horizontal, so the magnitude, the modulus of the slope is decreasing. So it's a graph with decreasing slope, and that means magnitude of the acceleration is decreasing. Magnitude of acceleration is decreasing here because the graph is becoming more and more horizontal. Horizontal looking graph means less slope, vertical looking graph means greater slope. So you're moving from greater slope to lesser slope, and that means acceleration is decreasing in magnitude. Now when I say slope is increasing or decreasing, I'm always going to talk about magnitude of slope, so the modulus of slope. I will not be looking at the sign of the slope here. In study of motion, this kind of works better, easier. So this is what we'll be doing. This is a graph with decreasing slope because it gets more and more horizontal. So magnitude of acceleration here is decreasing, while there is a downward sloping graph, so acceleration is negative. Another instance, V versus T, look at this graph. Now it's a positive slope, so acceleration is positive here, but as you notice, it's kind of more vertical here, it's closer to being vertical, and then it becomes more and more horizontal. And that means the slope is decreasing again. So magnitude of acceleration here is again decreasing. Now you can think of more possibilities. We have looked at possibilities where acceleration had a decreasing magnitude. We have other possibilities. Think of this kind of graph. Now it's a curve, so slope is variable, so acceleration is variable. But what you notice here is that the graph has a positive slope, and that means A, acceleration is positive. So we have a positive acceleration here. Also you notice the graph gets more and more vertical. So slope is increasing, and therefore magnitude of acceleration is also increasing. So graphs which are getting more and more vertical are those where acceleration increases, and graphs which become more and more horizontal, acceleration is decreasing. So have a look at a case where acceleration is negative. So you have a graph with a negative slope but increasing slope, and here acceleration is negative, but magnitude of acceleration is increasing because graph has an increasing slope. So magnitude of A is increasing. I remind you again, when I talk about slope increasing or decreasing, invariably I am talking about magnitude of slope and I'm not looking at the sign of slope. So when the graph gets horizontal, slope is decreasing, and when the graph gets more and more vertical, slope is increasing. So these are, I have shown, are the various possibilities of the VT graph. Now we're already aware that the slope of the VT graph equals acceleration at any given instant. So straight line VT graphs represent constant acceleration, curves represent variable acceleration. I have shown you the various possibilities there. So that's looking at the VT graph and working out acceleration from the VT graph. Now let's have a look at the AT graphs as well. We have already had a good look at the XT, that is the position time graphs. We know that the slope of the position time graph equals velocity. Then we had a good look at velocity time graphs. The area under the velocity time graph in a given interval equals displacement in that interval. And then the slope of the VT graph gives acceleration. We've seen that. And now we move to the acceleration versus time graph. So A versus P graph. In this graph, we plot A on the vertical axis and time on the horizontal axis. Now let's assume we have a graph that kind of looks like this. Now, what are the geometrical interpretations here? Now, dV by dt equals A. We take this dt onto the right hand side. dV equals A dt. Now let's integrate both sides of the equation. Let's say we start at time t1 and we continue integrating till time is t2. At time t1, let's say velocity was v1, and at time t2 velocity is v2. Here the limits of integration will be velocities because we are integrating with respect to velocity. So when dv is integrated, we get v, the limits being v1 and v2. And on the right hand side, or we might as well say vi initial and vf final. That kind of keeps it more meaningful. Initial, final. And on the right hand side, we have the integral of a dt from the initial point of time t1 to the final point of time t2. So what we have on the left hand side, when we, in place of v, we substitute vf and vi, the way we implement limits in integration, we get vf minus vi equals the integral of a dt from t1 to t2. So what we notice is that on the left hand side of the equation we have change in velocity. And if you remember the interpretation of integral as area under the graph, this integral is the area under the A versus t graph from time t1 to time t2. So the interpretation of the AT graph is that change in velocity equals the area under the graph. So if you are interested in calculating a change in velocity, simply calculate the area under the graph. So let's say this is time t1, this is time t2. During this interval from time t1 to time t2, if we calculate this area under the graph, this area equals change in velocity from time equal to t1 to time equal to t2. So this is the geometrical meaning of the A versus T graph. Simple enough. What we can do is take up a simple example. Let's say in a particular motion we are given the V versus T graph, and the graph looks like this. It's a straight line, and let's say this one, and we are told that at time equal to 10 seconds the velocity is 12 meter per second. Now I'm so sorry, this we were talking about acceleration time graph. So 12 meter per second square, that's the acceleration at time equal to 10 seconds. Now if you're interested in calculating a change in velocity during this interval, it's a straight line graph, so all you need to do is calculate this area, the area of the triangle, and that gives you the change in velocity. Let's say it is told that at time equal to 0, velocity, that is dx by dt, at t equal to 0 is 5 meter per second. And so let's calculate the area under the graph. That area is half into the base 10 into the height of the triangle, that's 12, and that's 60 meter per second. That's the area. Now this area 60 is equal to the change in velocity. Let's say velocity at time equal to 10 seconds is v minus the velocity at time equal to 0, which is 5. Change in velocity equals area. So the velocity at time equal to 10 seconds comes out to be 65 meter per second. So that's acceleration defined for you. What we will do now at this stage is that we will develop general equations for straight line motion, and those equations will involve calculus, some fairly elementary calculus, but if you're not familiar with calculus already, please go through my videos on calculus, where I have described differentiation and integration. Those videos are an absolute prerequisite for the study of motion in a straight line. So in case you're not familiar with calculus, please go through my videos on calculus. There is a playlist out there which talks about calculus, a set of I think 3 or 4 videos. Please make sure you go through that playlist, entire playlist on my channel. Coming back now to the equations for straight line motion. Well, the very first thing we'll start with is the definition of acceleration. Now acceleration equals dv by dt. So dv here equals a times dt. Now we can of course integrate. So we are integrating dv on the left hand side and integrating a dt on the right hand side. This starts with vi, the initial velocity, vf, the final velocity. Let's say when we started looking at motion, time was 0, and that's when velocity was vi. And then when time is t, velocity is vf. And so we have vf, dv integrated gives us v, and when we implement these limits, we have vf minus vi. I'm going fairly fast because we've just done this calculation a few minutes ago. And on the right hand side, we have a dt. Since I've gone fairly fast through this, of course, you always have the option of pausing and repeating what I just said. This is the first equation that we get. The change in velocity equals the integral of a dt from 0 time to t time. So that's the first equation of motion. We require integration to arrive at this. Now another thing we can do here is we can express a as dv by dx into dx by dt. I've just multiplied and divided by dx. Remember, this is v, and so we have a dx. We bring this dx onto this side. A dx equals v times this dv. Now we have v dv. I'll bring this to the left hand side, keep a dx on the right hand side, and now integrate both sides of the equation. V dv, we are integrating this, and on the right hand side we are integrating a dx. Now let's say vi is the initial velocity, and that's when the position x is x naught, and vf is the final velocity, and that's when the position is x. Now v dv integrated gives us v square by 2. If you recall, v to the power 1 we have here. When we integrate, we increase the power by 1 and divide by that increased power. The limits will be vi to vf, and on the right hand side we have the integral of a dx from x naught to x. So on the left hand side we have vf square minus vi square by 2, and on the right hand side we have the integral of a dx from x naught to x, and this becomes my second equation for straight line motion. So let's call this equation 1, let's call this equation 2. We can of course also arrive at one more equation, and that can be arrived at by using the v versus t relation. So let's say v is known as a function of time. We are aware of this. Usually that will happen here from the first equation. Now v of course is dx by dt, and that is equal to v. Take this dt onto the right hand side. Dx equals v dt, and then we integrate both sides of the equation. 0 to t, x naught to x. Dx when integrated gives us x, limits being x naught to x, and on the right hand side we have the integral of v dt starting with 0 time up to time t, And so we have x minus x naught, that's right, displacement. It equals the integral of v dt, 0 to t. So displacement equals the integral of v dt from 0 to t, which also comes from your interpretation of displacement being equal to the area under the v versus t graph. One example on the equations business, and then we are done with this section on straight line motion. You can take a screenshot at this time and then take your notes, and we then proceed. Now let's start with the simple example on straight line motion. Let's say, for instance, that we are given that acceleration A is 2t plus 1, where t is time. So this is variation of acceleration with time. At time equal to 0, x is, let's say, 0, and dx by dt, that is velocity at time equal to 0. This is just notation stuff, dx by dt with a bracket, t equals 0. This means dx by dt at time equal to 0. So that's the initial velocity. This is given to you, let's say 5 meters per second, and we are asked to calculate velocity and position as functions of time. So to calculate velocity and position as functions of time, let's start with this equation. A is dv by dt, it equals 2t plus 1. We take dt onto the right hand side, and we have dv equals 2t plus 1 dt. Let's now integrate both sides of the equation, 0 to t, and at 0 time the velocity was 5. At time t, let's say the velocity is v. So on integrating dv, we get v from 0 to v, and on the right hand side we have the integral of 2t plus 1 dt. The integral becomes 2 into t dt integrated from 0 to t, plus 1 into dt integrated from 0 to t. Now initial velocity wasn't from 0, it was 5. So on this side of the equation we have v minus 5, on the right hand side 2. T dt integrated gives 2t square by 2, dt integrated gives t, and we have limits 0 to t. So v minus 5 equals 2 cancels, and you substitute t and 0, you have t square. Again substitute t and 0, you have t minus, substituting 0, you get 0. So v now equals 5 minus t plus t square. So we already have the v versus t relation. The next relation that we need to find out is the relation between x and t, and that starts from here. We now have v versus t. So this v, of course, is dx by dt. It equals 5 minus t plus t square. Let's take dt onto the other side. dx equals 5 dt minus t dt plus t square dt, and then we integrate both sides of the equation. Dx integrated on the left hand side, on the right hand side 5 into dt integrated minus t dt integrated plus t square dt integrated. Limits for time 0 to t, 0 to t, 0 to t, and limits for x at time equal to 0, x was 0, so we start with 0, 0 time, x is 0, t time, it's x. So dx integrated gives us x, we implement these limits, we end up with x on the right hand side, 5, dt integrated gives t, 0 to t, minus t dt integrated, t square by 2, 0 to t, plus t cube by 3, 0 to t. So we now have x equal to 5. Now you substitute t in place of t, you get t. You substitute 0, you end up with 0. So you have 5t minus, again, t square by 2 minus 0 square by 2 plus t cube by 3 minus 0 cube by 3, that's t cube by 3. So you now also have the relation between x and t. So this is a general workout on acceleration and the relations between v and t, x, t, and a and t. In our next session, we will have a focus on what we call the uniformly accelerated straight line motion. And uniformly accelerated straight line motion is actually motion with a constant acceleration. That's the topic for our next class. In that class, we'll be looking at uniformly accelerated straight line motion, which means motion with a constant acceleration. We will be looking at the graphs that are used to represent it and how those graphs are used, how those graphs are interpreted and then used for solving practical problems from everyday lives. Thank you so much for watching this. Please take your screenshots and take your notes. Thank you very much.